Now we will move to a different type of talks. And as I said at the beginning, this is something really exciting. It's about insights and lessons from negative results. And as we said at the beginning, always with those negative results, there's many lessons to be learned. And today we have two very exciting talks. The first one from Avi Ziv, lessons from machine learning based triage. He is actually a doctor engineer. He's a member of the Hyper Cloud Quality Technologies Department at IBM Research Haifa Lab in Haifa, Israel. He has a long experience in developing methodologies, technologies, tools for hardware functional verification, including more than 2 decades of work on data analysis and machine learning hardware verification. And I do believe for more than 2 decades of such a great experience, there's many lessons have been learned, and we are looking forward some of them from you today. Thanks for joining us. Avi, I think you are muted.
Okay, can you hear me now?
Yes, perfect, thanks.
Yes. Okay. So again, thanks for the introduction and for explaining what this session is all about, which will save me some time. And also I would like to thank Shop on the great introduction on verification and challenges. This will also save me some time. But what I'm going to talk about again is about lessons from work we did on machine learning-based triage, which didn't gave us the results that we were hoping for. So maybe an alternative title for this talk is we tried machine learning-based triage and failed. What are our excuses? And the outline here is, first I'm going to explain what triage is and what triage means in the world of hardware development process. And then I'm going to talk about how we can look at triage as a machine learning problem. And actually the mapping there is quite natural. And then I'll talk about our triage attempts, show some results. This is going to be actually fairly brief, so I'm not going to go into much detail about this. And that will hopefully give you some time to talk about the lessons learned, why we believe triage is so difficult, and finally answer the question, is there hope? So do we believe that we will be able to use automatic techniques for triage and specifically machine learning-based techniques? So if we talk about triage, triage is actually a term that comes from the medical domain. It's the process that is done when you have several people who need attention and you don't have enough resources to give the full attention to everybody, and then you want to quickly assess their condition and the likelihood that, well, first of all, they recover or something bad is going to happen to them if we are not going to treat them soon, or how soon do we need to treat them. And then the question is how this is related to hardware development, or actually in the same way to software development. So in the domain of hardware development, triage is a pre-debug process that handles a set of failures. For example, we have a nightly regression run that produces many fails, and then the verification teams come in the morning and want to decide what they need to do about it. So the goal of the triage is to set a set of traits for each failure to simplify the efficiency of the handling of the failures and increase the quality of handling them. And that means several things. So the important triage activities include, first of all, we want to determine for each failure how severe it is. Is it something that's going to hurt our chances for to have a successful tape out? Is it something that's going to block our efforts to verify parts of the design and so on. So we want to determine this. And we want to find who is the right person to handle the failure. And those two things are actually very much similar, like what the medical triage is. We want to give priority to handling failures, and we want to find the right person in the medical domain. It's the right doctor, the right, is it orthopedia, is it something else? And we want to do those, but there are two other items that are not that common to the medical domain. And first of all, we have many failures, but some of them are coming from the same root cause. We want to cluster together all the failures that are coming from the same root cause, because it's usually enough to handle one of them, fix the root cause, and then all the rest of them will be fine afterwards. The second thing is, if we have failures that we already know that the root cause, or we already found an example of this root cause in the past, we want to associate the new failures with the known issue that we had, and therefore save us time doing duplicate debug work. Those two things are, well, unique to the development process triage, and actually those are the two items that I'm going to focus in the rest of the talk. So what has triage has to do with machine learning? So even from the words that I described the task earlier, we can see that many of the activities naturally map to traditional machine learning techniques. So for example, if you want to identify failures with a known issue, this is a simple classification problem. We have a classifier, we have labels for all the known issues that we have, we put a new failures, and we classify it to the right issue. So this is a simple case of supervised learning. It's actually not that simple case, because there are many, or some at least, items that are not going to have any label at all, because they are new. There are new root causes, there are new issues that we haven't seen before. The second thing, we want to cluster failures with the same root cause. So as the name suggests, this is clustering. So this is an unsupervised learning. We want to take a group of or a set of failures. We want to run a clustering algorithm on them, and then get basically a cluster for every root cause, and then we can continue with the triage debug process. We can do a little bit more here, but again, this is not in the scope of the talk. For example, if we find those clusters, we can also maybe identify the test or the failure in there that's going to be the simplest to debug. For example, the failure happened the earliest, or the scenario around it is the simplest, and so on. So this will help the debugger. But again, this is outside the scope of this presentation. The other things that makes triage a natural candidate for machine learning is that we have plenty of data to work with. First of all, and I would say, unfortunately, we have many failures. So we have many failures to work with. And again, if I take IBM as an example, for just one environment, we can have thousands of failures every day. So we do have a lot of data. Label data is a different story, and I'm going to talk about label data in several places during this presentation. So for now, let's just leave it that label data is a different story. And not only that we have many data items to work with, we also have rich data for each failures. So each failure has a lot of, I would call it metadata, like the test name and the model of the hardware it ran on and so on. It also has simulation traces, simulation logs, so a lot of files that contains, again, a lot of information, and all of this can be used for the learning process. So overall, it seems that looking at triage, it is a natural candidate for machine learning techniques. And one other thing that I can add is that triage is also a very important problem. So if we talked, Shobha talked that verification is nowadays is something that is highly automated. We can generate a lot of tests. We have a lot of tools that help us doing things. Debug and triage are one of the main manual bottleneck that requires a lot of man time, a lot of human interaction, a lot of expertise in order to do it in the right way. So if we can add automation, either replace the human triage with a machine learning system, or even provide some assist tools to the human triage, we can improve the quality of the process a lot. So what did we do? What are our triage experiments? So first of all, what we try to do is analyze new failures of a given environment. So we have an environment, most of the data that I'm going to show here, the little data that I'm going to show here, is going to be about the processor core of a high-end system developed in IBM. And new here in quotation mark, because it wasn't really new data, it was old data that was kept, but we treated it as new data, and I'll explain later what I mean by new data. The goals actually that we have are basically what I described earlier. So we want to identify failure that share root cause with existing issues or tickets or whatever name you want to use for something that already was seen, marked as something that needs to be taken care of and is somewhere in Bugzilla or whatever bug tracking system you have. We also wanted to identify failures with new root causes, and we want to cluster them according to the root causes. So basically the classification clustering that I mentioned earlier. So if this is an example, we have already existing 3 issues for the red, purple, and green ones, and we have all the dots in the right side riding. So we want to take the 2 red dots and assign them to the issue 1, the 3 purple assigned to issue 2, and the 4 yellow one are new root cause we want to open. Again, I'm not saying if this is something that's done automatically or just we tell a person do open a new ticket or new issue for this one, and the blue one is going to go to another one. The analysis we did is time-based analysis. So we trained the system on data of 14 days, and then we test it on the next day, on the 15 days, and that's why we said I said the new failures. So we have 14 days of history. Now the new failures come. We want to take them and use the history to do the triage, the automatic triage. So this looks very simple, but let's look a little bit about the reality of things. And the first thing, and here I go again to label data, is that label data is actually very hard to get. And it's very hard to get because manual labeling requires a lot of expertise and a lot of time, and therefore we do not expect to get a lot of manual labeling. So if we look at the classical machine learning, we see, for example, if we look at the ImageNet or something like image processing, their labeling is fairly easy. When you go to some sites, it asks you to make sure that you are a human. It asks you to label pictures, and the user collect this data and use it as labels. Of course, it collects majorities and so on. Even if you look at more sophisticated data, like observing CT images and try to decide whether there is a cancer in them, when you need an expert, you need some radiologists to do that. There are a lot of radiologists that can do the work, so if you give each of them a small number, they can give you a large set of data, of labeled data. Here we have, I don't know, 3-4 experts who can do this labeling, and each labeling takes, I don't know, something between few minutes to maybe hours of work. And therefore, we cannot ask them to do that much labeling, and therefore, we don't have a lot of labeled data. And in our case, the example with most labeled data that we have, which is the core of this, the processor core that I mentioned, we have about 10% of the data labeled, 90% of the data was never labeled. So we cannot work actually with that. And I'm going to talk about automatic labeling later. Also, the second fact that we have is that not all failures are born equal. First of all, you must know that the main characteristic of failure is the error message that we get. And for most error messages, there is almost 1-to-1 or maybe small n-to-1 relation between the error message and the root cause. So if I see two failures with the same error message, they are coming from the same root cause. If I see them coming from a different error message, they most probably coming from different root cause. And again, this is at a given point of time. When time changes, this labeling is not correct, but the windows we had is small enough for this to hold. But there are some exceptions to this rule, and those are the generic error message, like, I don't know, you have a timeout. So you run simulation and never finished, so something bad happened, or a data miscompare. You read and the data is not the real data you're expecting. This is something that is much harder, and many different root causes can lead to this kind of error message. So if we look at the distribution, we see that more than half of the failures that we have are coming from those hard error messages, and therefore difficult to triage failures, and only 40% coming from the others. But if we see what happened in the label data, we also see that distribution is completely different. We have very small percentage coming out of timeouts, which means that not only that we have small amount of label data, this label data is also not very representative of the real world. And finally, how do we measure the quality of the results? And here we have two issues. One of them is that, okay, we have two bad outcomes of triage. First of all, we lose important failure, we don't treat it, and it's gone lost, and this is actually a bug that don't happen a lot, but it's very important. Or the other end is that two teams are working on the same root cause and we waste effort. They are not easily mapped to a measure that we know, like accuracy, precision, and so on. The other thing is that what number is good enough, even if, let's say, we use F1 score, is 80%, 0.8 result is good, or whatever. So this is the reality. And as of the flow, so we have a lot of data. As I said, we have the structured data, like the error message, a test name, the failing cycle, and we have the simulation trace. And we have a lot of machine learning techniques that we used. Not in all of them we used all the data. Specifically, in many experiments we didn't use only the trace, and I'll talk about it a little bit. Several techniques to process the simulation trace. We use several techniques like bag of words, bag of sentences, and many other, I would say, standard text processing techniques. And we use several machine learning algorithms like neural networks, multi-class classifier, several clustering algorithms, and so on. And I'm not going to go into details. But here are the results. We have on the left side the clustering results and how good they are based on the type of failures. And we can see that for the hard failures like timeout and the miscompare, the results are less good than the overall results. On the right side, we have the classification results for different algorithms that we use. And again, I'm not going to go into details. We see that in some cases it's fairly high, in other cases it's not. So what are the conclusions, the immediate conclusions for that? Well, first of all, if you look at the results from high above, it looks respectable. It's not great results, but it's not bad results. But if we take a closer look, we see that actually the results are not that good. For example, we have low accuracy in the difficult error messages, where actually it's important and hard to do the triage. Also, we already have a simple rule-based system that basically added the triage engineer add rules as he understands more about the failures, and it's do the classification automatically based on that. And our machine learning techniques did not perform much better or even better than this simple rule-based system. And finally, and this was rather surprising, that the simulation traces actually did not help us improve the results of the triage that we did. And as I said, this was rather surprising because the way human beings are doing triage is looking at those traces, and those traces contains all the information, or I would say 99% of the information that needed for triage, and most of the information that needed for debug. So why didn't they help? So with that, we come to the interesting part of the lessons learned, and it divided into few parts. First of all, we need to understand that actually the world is against us. And the world is against us for two reasons. First of all, verification. The nature of verification is actually a chaotic process. It's trying to create chaos inside the design. It's trying to create as much noise as possible because this is the way you discover bugs. Machine learning tries to discover commonalities, to generalize by analyzing the data, and it knows how to ignore noise, but only to some extent. And I believe that the noise that verification can create can be much stronger than the level of noise that the machine learning, or at least the machine learning that we try, can handle this. And therefore, any verification task that tries to analyze and understand what happened in a run is going to suffer from this kind of a bad effect. Also, if we look at the development process, we also see that it's against us because everything is continuously changing. So our data is continuously drifting, and it's drifting fairly fast. If we are using continuous integration techniques, we can have new models several times a day. We can have bugs disappearing, new bugs appearing, feature activating, and start testing. So the data of yesterday cannot tell us a lot about what's happening today. So this is also not very helpful in triage. But also there are things that we can do better. First of all, the problem of the labeled data. I talk about why manual labeling is hard, but maybe we can use automatic labeling. This is also something that is difficult. It's not accurate, again, because of the drifting or the changing nature of the process. But maybe we can do better there. And also, we need to find a better way to utilize the simulation trace. And there, our problem was that basically what we use are generic document and test processing techniques, and those are not sufficient. They are not sufficient to understand what's happening in the test, and therefore they cannot be very helpful in assisting the automatic triage. Again, we can do better because those documents are actually have, in a lot of cases, semi-structured data that can be used and so on, and I will talk about it at the end. Finally, there are other factors that we need. Our success threshold is very high. First of all, as I mentioned, we have the existing solution, and also we have expert users who demand very high quality solutions, otherwise they will not use it. And finally, and I think that Shir talked about it on Monday, that we don't have benchmark that we can compare ourselves. So again, how do we measure results? So let's finish by asking the question, is there hope? And Sakin on Tuesday talked about what happens when you have a question mark. That means that the answer is no. But since you expect the answer to be no, of course, the answer is going to be yes. And I guess the answer is yes, because otherwise I wouldn't be motivated to give this talk. I wouldn't think that this talk is something that should be given to such forum. First of all, we can work on the things that we can do better. We can do better labeling. It will require maybe a lot of compute resources. I'm not sure that it will require a lot of sophisticated algorithms, but we can do that. But what's more important, we can better understand the simulation trace. And again, if I go to Shobha's talk earlier today, the way to understand what the design is doing and what the design is doing on specific stimuli using, for example, DNN, can provide us help to understand what happened, and then to understand that we have an anomaly that represents the bug there. And if we can do that, we can do it in use it in many other places. And again, Shobha gave us a lot of examples. And again, this can help us fight against nature, because it can help us reduce and tame the noise. The big question is this going to be cost effective? So if we're going to have to spend 10 years for each project to build our triage system, it's probably not worth the effort. But if you can find things that can help us build a fairly easy automatic triage, then yes, it worth the effort, and therefore I think we should continue this work. So thank you for your time, and I guess maybe we have time for a few questions.
Avi, thanks a lot for the great talk. Just to make sure you hear me, right? Thanks, Avi, for the great talk. Do you hear me now?
Yes, I can hear you.
Okay, it seems like unless you remove the share screen, I'm still muted. Thanks again. So really great talk and great lessons. we don't have questions from the audience, but I have one question. So you mentioned that the simulation results did not help to improve, and you said this is surprising. I'm not sure if I missed it, but I still don't understand why it did not help in this problem.
Well, I don't know why it did not help. Well, all I say that we did experiments with one set of features, which was only the structured data features, and another set of experiment with another set of features that included the trace, and the results were the same. So that's why. So it's an observation. It's not a conclusion. As for the why it happened, I think that because we treated the trace the wrong way. We basically treat the trace as a text document, and then we says, okay, in text documents we can compare them using bag of words techniques, terms frequencies, and all those kinds of techniques. And those techniques are not good enough because, again, we have a lot of noise which is going to make the documents really different, and we cannot find the commonalities and then the small deviations from where the commonalities should continue. So
okay.
we should look for ways to better utilize the trace, and then I'm sure that if we find those ways, we will be able to use the trace.
Okay, great. Thanks again, Avi. And for the audience,
Avi, just a quick question following Hussam. Is it in another way, in machine learning terms, saying that we need a better way to extract features from the trace?
Yes, you can say that it's a better way to extract feature from the trace. But maybe, again, maybe we lead to something which is not really features. So I don't want to limit myself to those kind of terms.
Okay, sounds great. Okay, thanks again, Avi. And for the audience, if anyone has questions,